NASA engineered a $2 sheet that cuts attic heat by 25 degrees. Oak Ridge National Laboratory proved it. Your building code pretends it doesn't exist. Fiberglass insulation runs $2,000 to $5,000 installed. Full attic radiant barrier coverage costs $50 to $100 in materials. You can do it in one afternoon with a staple gun. By the end of this video, you'll know exactly how to install NASA's passive cooling technology in your attic. You'll understand why the building code buries it, and you'll see why it's the single most important modification for surviving a grid-down summer. That's not marketing. That's a government laboratory measuring a 97% radiant heat reflectivity rate in real homes, in real summers, exposed to real sun. And the entire insulation code in this country uses a metric that physically cannot measure what this material does. To understand why you've never heard of this, you need to understand one number and the industry that invented it. Welcome to the channel. What we do here is simple. We find knowledge that institutions bury, sometimes through neglect, sometimes by design. We verify it against the best available evidence, and we teach it, plain language, no gatekeeping. If that matters to you, subscribe. You're not joining a fan base. You're joining a research community. And this video is a perfect example of why that community needs to exist. Let's start where this technology was born, 240,000 miles from the nearest building code. In the 1960s, NASA had a heat problem. The Apollo Command Module re-entered Earth's atmosphere at roughly 25,000 miles per hour. At those speeds, the heat shield faced temperatures exceeding 5,000 degrees Fahrenheit. But the spacecraft also faced a subtler challenge during the transit itself. In the vacuum of space, with no air to conduct or convect heat, radiant energy from the sun was the dominant thermal threat. NASA engineers needed lightweight, passive protection. No moving parts, no electricity, no maintenance. They developed multi-layer reflective insulation systems, thin sheets of metallized material separated by air gaps. The principle was elementary physics, executed at an extraordinary level. Here's the science, and it matters. Heat moves through your home in three ways: conduction, convection, radiation. Conduction is heat traveling through solid material. Touch a hot pan. That's conduction. Convection is heat moving through air or fluid currents. Hot air rises. That's convection. Radiation is heat traveling as infrared energy. It doesn't need contact. It doesn't need air movement. It crosses empty space at the speed of light. The sun heats your roof through radiation. Your roof absorbs that energy. It re-radiates it downward into your attic. Your roof becomes a radiant heater suspended directly above your living space. A reflective radiant barrier intervenes at exactly this stage. Installed on the underside of your roof rafters with a small air gap, it reflects up to 97% of that radiant energy back toward the roof. The heat never reaches your attic floor, never reaches your insulation, never reaches your ceiling. Emissivity is the key property. It measures how much radiant energy a surface releases. Polished aluminum has an emissivity of roughly 0.03. It absorbs almost nothing. It emits almost nothing. That's why NASA used it in space. That's why it works in your attic. The physics are identical. But here's the critical detail. That air gap is essential. Lay a radiant barrier flat against the roof deck with no gap, and you eliminate the radiant mechanism. It becomes a conductor. The airspace is what allows the barrier to reflect rather than absorb. This is not optional. It's the physics. Rating a radiant barrier by R value is like rating a flashlight by its weight. Then concluding it produces no light because it's only 6 ounces. So NASA built it. The DOE tested it. Here's what they found. Before we get into the government data, a quick word about the vault. What you're watching right now is the surface of our research. The vault goes deeper. Grid-down energy systems, water purification methods most people have never encountered, food preservation techniques that predate refrigeration by centuries, medical preparedness, communications when the grid fails, no fluff, no filler. Every entry is sourced and verified the same way this video is. Link is in the description. But stay right here. Everything you need to install a radiant barrier is in this free video. Nothing is held back. Now let's talk about the government data that proves this works, and the measurement system that pretends it doesn't. It was Oak Ridge National Laboratory, that's the DOE's premier building science research facility in Tennessee, conducted field studies on radiant barriers in residential attics. Not in a laboratory, in real occupied homes in southern climates. They measured attic temperature reductions of 15 to 25 degrees Fahrenheit in summer consistently. The data was published, the methodology was peer-reviewed, the results were replicated. This is not fringe science. This is the United States Department of Energy validating a passive thermal technology with no moving parts and no energy input. 15 to 25 degrees cooler in your attic for under $100. Now, here's where it gets interesting. And by interesting, I mean infuriating. The R value system is the standard metric used in American building codes to rate insulation performance. Every building in this country must meet R value minimums set by the International Energy Conservation Code. Your contractor quotes R value. Your building inspector checks R value. Your homeowner's insurance assumes R value compliance. R value measures resistance to conductive heat transfer. Only conductive heat transfer. It quantifies how well a material slows heat moving through solid contact. Fiberglass is excellent at this. Cellulose is excellent at this. Spray foam is excellent at this. Radiant heat transfer is a completely different physical mechanism. R value does not measure it poorly. It does not undercount it. It physically cannot measure it, by definition. The metric was never designed to capture radiant resistance. Or asking what R value a radiant barrier has is a category error. It's the wrong question applied to the wrong physics. A radiant barrier reflecting 97% of incoming radiant heat receives negligible R value credit under the IECC, negligible. A technology validated by Oak Ridge National Laboratory effectively does not exist in the building code's measurement framework. This is not an accident of history. The R value system was developed and aggressively promoted by fiberglass insulation manufacturers. Owens Corning, the single largest fiberglass insulation producer in North America, was instrumental in establishing R value as the standard metric. They lobbied for its adoption in building codes. They funded the research that centered it. They built an entire industry around a number that, by pure structural coincidence, makes their product the only viable compliance path and renders the cheapest alternative invisible. I want to be precise about this. Whether this constitutes deliberate suppression or institutional inertia is debated. I'll address that directly in a moment. But the structural outcome is not debated. A measurement system built by fiberglass manufacturers governs every home in America. That system cannot see radiant barriers, and radiant barriers are the only technology that threatens the fiberglass installation business model. So let's put real dollars on what this regulatory blind spot costs you. Professional fiberglass insulation for an average attic runs $2,000 to $5,000 installed. That includes materials, labor, and disposal of old insulation if needed. It's a significant home improvement expense. Most homeowners finance it. A radiant barrier for the same attic costs $50 to $100 in materials. The sheets themselves run roughly $2 each. You need no specialized tools, a staple gun, a utility knife, a headlamp. You need no contractor, no permit in most jurisdictions, no inspection requirement. One afternoon, one person, under $100. The fiberglass industry sells to every code-compliant home built in America, every single one. That is a guaranteed market created by regulation. A builder cannot pass inspection without meeting R value minimums, and R value minimums can only be met with conductive insulation products. The code does not recognize the alternative. Now consider the competitive math. What if homeowners widely understood that a $100 afternoon project could reduce attic temperatures by 15 to 25 degrees? What happens to the $5,000 installation market? If builders could get radiant barrier credit toward code compliance, what happens to the fiberglass requirement? No corporation spends marketing dollars telling you about aluminum sheets. There is no radiant barrier industry lobby. There are no radiant barrier advertisements during home renovation shows. There is no profit margin that funds awareness campaigns. The product costs $2. You can't build a marketing empire on $2 commodity sheets. The technology wasn't banned. It wasn't discredited. It was defined out of existence by a measurement system built by its competitors. If this kind of research matters to you, the kind that names names and shows the math, subscribe. Share this with someone who pays an electricity bill. The vault link is in the description for those who want the deeper archive. But stay right here, we're not done. Before I show you exactly how to install this, I need to be honest about what it can't do. Radiant barriers address radiant heat transfer only. They do not slow conductive heat transfer. They do not stop convective air movement. In a heating-dominated northern climate, where most winter heat loss is conductive through walls and ceilings, a radiant barrier provides significantly less benefit. This technology delivers its greatest performance in southern and sunbelt climates, where summer cooling loads dominate energy costs, and where the sun drives intense radiant heat through the roof for months. Humidity matters. In climates with high humidity, an improperly installed radiant barrier can create a condensation surface. Moisture collects on the cool side of the barrier and can drip onto insulation below. This is a real risk. The solution is straightforward. Use a perforated radiant barrier product. The microperforations allow moisture vapor to pass through while still reflecting radiant energy. In humid climates, perforated product is not optional. Dust accumulation reduces reflectivity over time. This is mitigated by installing the barrier with the reflective face pointing downward. Gravity keeps the reflective surface clean. Upward-facing installations lose effectiveness as dust settles. The backing material on most radiant barrier products is combustible. It will not start a fire, but it will burn if exposed to flame. Know this, keep it away from heat sources in the attic. exhaust flues, recessed lighting cans, anything that generates concentrated heat. A radiant barrier does not replace your existing insulation under current building codes. It supplements it. Do not remove your fiberglass or cellulose. Add the barrier above it. These are real limitations. Knowing them makes you more competent than most installers. Now that you know what it does, what it doesn't do, and why nobody told you about it, here's exactly how to install it. Materials. Radiant barrier sheeting. Sold in rolls at most home improvement stores. Look for 96 to 97% reflectivity rating. Reinforced aluminum facing on both sides is ideal, but single-sided works. In humid climates, buy a perforated product specifically. Total material cost for a typical 1,500 square foot attic, $50 to $100. You also need a staple gun with 3/8 inch staples, a utility knife, a headlamp or work light, and a dust mask. That's it. Step 1. Access your attic in the early morning or evening. Never work in an attic during peak heat. Temperatures can exceed 140 degrees Fahrenheit in summer afternoons. Bring water. Step 2. Unroll the radiant barrier sheeting along the underside of the roof rafters. Reflective side faces down toward the attic floor. This orientation maximizes reflectivity and minimizes dust accumulation. Step 3. Staple the sheeting to the underside of the rafters, not flat against the roof deck. The barrier must hang from the rafters with an air gap between it and the roof sheathing. This air gap is where the physics happens. Without it, you have an expensive piece of aluminum touching wood. With it, you have a radiant heat mirror. Step 4. Overlap each sheet by 2 to 3 inches at the seams. Full coverage matters. Gaps allow radiant energy through. Think of it as light. Any opening lets it pass. Step 5. Do not cover soffit vents, ridge vents, gable vents, or any other ventilation openings. Attic ventilation is critical for moisture management and code compliance. The barrier goes between the rafters. It does not seal the attic. Step 6. In humid climates, confirm your product is perforated. Run your hand across it. You should feel tiny holes. If the product is solid foil with no perforations, do not install it in a high humidity environment without additional ventilation planning. Step 7. Inspect your work. Look for continuous coverage across the entire roof underside. Check that the air gap is maintained everywhere. Verify no ventilation is blocked. The whole process takes one person a single afternoon. Step back and look at what you just did. You installed the same radiant heat management principle that NASA engineered for the Apollo spacecraft. The Department of Energy tested it. Oak Ridge National Laboratory measured 15 to 25 degrees Fahrenheit of attic temperature reduction in real homes. It cost you less than dinner for two. And the reason you've never heard of it is that the measurement system governing every home in America was designed by the people selling you the expensive alternative. This is one of the only insulation technologies that works with zero electricity. No fan, no compressor, no thermostat, no grid connection. In a prolonged power outage during a summer heat event, the exact scenario that kills people, your attic is still 20 degrees cooler. Your ceiling is still bearable. Your home is still survivable. For $100 in an afternoon, you now know something most homeowners don't, most contractors don't, most building inspectors don't think about, and it cost you 20 minutes. Share this video with someone who lives in a hot climate. Share it with someone who worries about the grid. Share it with someone who just paid $5,000 for insulation and never heard the word emissivity. Next week, we're opening another entry from the vault, another technology with government validation and zero marketing budget. Another thing that works, costs almost nothing, and somehow never comes up. Subscribe so you don't miss it.